Welcome to This Explainer. Today, we're going to unpack something really cool, the fascinating invisible mathematics that gives machines the ability to, essentially, see, compare, and understand data. It's the hidden geometry running inside almost every AI model we use today.
Have you ever actually thought about this? I mean, machines don't have eyes, right? When they look at a picture of a cat or a massive cluster of customer data, they just see giant arrays of numbers. So how in the world do we teach a computer the human concept of similarity? How does an algorithm know that one piece of data is like another?
Well, the secret sauce is analytic geometry. By translating real-world objects into high-dimensional vectors, we basically give the computer a spatial environment to work within. Once our data is converted into vectors in this mathematical space, we can finally start measuring them.
Okay, let's dive right into this. Here is our roadmap for today. We'll start with 1. Defining similarity for machines. Then move to 2. Inner products and norms. 3. Angles and orthogonality. 4. Orthogonal projections explained. And finally, 5. Powering machine learning.
Take a look at this visual map for a second. Notice how absolutely everything cascades from one single core concept, the inner product. From the inner product, we cascade down to norms and lengths, which then lead to angles and orthogonal projections. And as you'll see, these geometric engines directly drive the dimensionality reduction, regression, and classification algorithms we use all the time.
Section 1. Defining similarity for machines. Turning objects into comparable math. We need a rigorous, quantifiable way to compare two vectors.
So why does this matter? Well, as this quote points out, the entire assumption of predictive machine learning is that similar inputs should yield similar outputs. If a computer can't mathematically calculate similarity, the whole concept of a predictive algorithm just completely breaks down. We desperately need a way to measure the distance between these data points.
Section 2. Inner products and norms, the engine of space and scale. This brings us to the actual mathematical engine used to calculate that similarity.
So what is an inner product? Basically, it's an operation that takes two vectors as input and spits out a single numerical value representing their similarity. And what's crucial here is that an inner product naturally creates what we call a norm, which is just the mathematical term for the length of a vector. According to the Cauchy-Schwarz inequality, this specific operation is exactly what allows us to calculate distances in high-dimensional space in the first place.
Now, what's really interesting about this is that the geometry of the space actually changes depending on which mathematical definition of the inner product we choose to use. Most of us are used to the standard dot product, which gives us standard Euclidean distance. But actually, scratch that. That's just one type of inner product. If we define a non-standard inner product using a different matrix, the very fabric of our data space literally morphs.
Let me prove it to you with a textbook example. Take the 2D vector 1, 1. If we use the standard dot product, the length of this vector, its norm, is 1.41, or the square root of 2. But if we swap in a specific non-standard inner product matrix, the length of that exact same vector becomes exactly 1. The data hasn't changed at all, but our mathematical lens has. It proves that our choice of math alters the machine's reality.
Section 3. Angles and orthogonality. Figuring out orientation. Inner products don't just give us the length, they also give us the angle between two different vectors.
And this brilliantly illustrates just how mind-bending this math can be. Look at these two vectors, x and y. On the left, using the standard dot product, the angle between them is exactly 90 degrees, a perfect right angle. But on the right, for the exact same vectors, if we apply a different inner product matrix, the angle shifts to an obtuse 109.5 degrees. Orientation is entirely relative to the inner product we select. Crazy, right?
This leads us to a super vital concept, orthogonality. Two vectors are orthogonal when their inner product is exactly 0. You can kind of think of orthogonality as the high-dimensional generalization of perpendicularity. For a machine learning model, discovering that two vectors are orthogonal is a huge deal. It means those two data points or features are completely unrelated and independent from one another.
Section 4. Orthogonal projections explained. Casting high-dimensional shadows. How do we deal with overwhelmingly complex data? We compress it.
In machine learning, we're often dealing with data that has thousands of dimensions. It is completely impossible to visualize and incredibly computationally heavy. So we solve this by projecting that data down onto a lower dimensional subspace. The math can seem daunting, but it really just breaks down into 3 logical steps. First, you find the coordinates for your new subspace. Second, you calculate the specific projection point. And third, you find the projection matrix that can linearly map any vector over into this new, simpler space.
Think of it visually like casting a shadow. Imagine that gray plane, U, is our simpler feature space, and the yellow arrow, X, is our complex, high-dimensional data point. By dropping a perpendicular line straight down to the plane, we create the red vector, the orthogonal projection. We're essentially casting a shadow of our complex data onto a simpler plane. The distance of that drop? That's our reconstruction error. We use orthogonal projections specifically because they minimize this error, meaning we lose the absolute least amount of information possible.
Section 5. Powering Machine Learning, the climax of geometric tools. It's time to tie all these abstract building blocks together.
So the crucial point is this. The most powerful algorithms in data science are secretly just engines of analytic geometry. Support vector machines? They classify data by finding the optimal hyperplane to separate classes, which relies entirely on inner products and norms. Linear regression predicts outcomes by minimizing orthogonal distances, and principal component analysis, or PCA, manages massive datasets by finding the most informative dimensions and utilizing those exact orthogonal projections we just looked at to compress the data.
We've seen how machines use math to build their perception of similarity. But remember what we discovered earlier. Changing the inner product matrix literally changes lengths and angles. It reshapes reality for the machine. So I want to leave you with a fascinating thought. If shifting our mathematical definitions changes the very shape of the data space itself, what entirely new ways could AI perceive the world and solve complex problems if we simply re-engineered our definitions of distance? Thanks for joining me on this explainer. I hope it changed how you see the math behind the machine.